introduction. The food we eat, the clothes we wear, the cosmetics we use, the fuels we use to run automobiles are all the compounds of carbon. Carbon was discovered in prehistory and it was known to the ancients. They used to manufacture charcoal by burning organic material. Let us know about the carbon. Carbon is a non-metal. It belongs to the 14th group or 4A group in the modern periodical table. The elements of this group have 4 electrons in the valence shell. Atomic number is 6. Electronic configuration of carbon: 1s2, 2s2, 2p2. To get the octet in its outer shell, it has to gain 4 more electrons to form C4-. Its nucleus has only 6 protons. Therefore, it would be difficult for a nucleus with protons to hold 10 electrons. Hence, carbon cannot form C4- ions so easily. If carbon loses 4 electrons from the outer shell, it has to form C4+ ions. This requires huge amount of energy which is not available normally. Therefore, C4+ formation also is remote possibility. Carbon has to satisfy its tetravalency by sharing electrons with other atoms. It has to form 4 covalent bonds either with its own atoms or atoms of other elements. Example: the possibility of bonds formation by a carbon atom is as 4 single covalent bonds with atoms of same element like chlorine element, 4 single covalent bonds with atoms of different elements. Carbon atoms may form 1 double bond and 2 single bonds. Carbon atom may form 1 single bond and a triple bond. Example: HC forms triple bond with CH, or CH3C forms triple bond with N. Or carbon atoms may also form 2 double bonds as CH2 forms double bond with C and C forms double bond with CH2. As per valence bond theory, the 4 unpaired electrons in a carbon atom are shown by suggesting excited state to carbon atom. Brown state: electronic configuration of carbon: 1s2, 2s2, 2p2, or 1s2, 2s2, 2px1, 2py1, 2pz0. Carbon. Ground state: excited state, electronic configuration of carbon: 1s2, 2s1, 2px1, 2py1, 2pz1. Carbon. Excited state. We have to understand that free carbon atom would not be in excited state under normal conditions. In excited state, carbon atom gets its one of the 2s electrons to say 2pz. Each carbon atom has 4 unpaired electrons when excited. We have found that in excited state, carbon atom has 3 unpaired electrons in p orbital and 1 electron in s orbital. These 4 valence electrons are with different energies. When the carbon atom tends to form 4 bonds with other atoms. The energy required for excitation is taken up from bond energies, which are the liberated energies when bonds are formed between carbon atom and other atoms. In methane CH4 molecule, one carbon shares 4 electrons with 4 different hydrogen atoms, one each of different hydrogen atoms. It shows carbon is tetravalent because it possesses 4 valence electrons, and hydrogen is monovalent because it has only one valence electron. Example: CH4, promotion of electron. When bonds are formed, energy is released and the system becomes more stable. If carbon forms 4 bonds rather than 2, still more energy is released, and so the resulting molecule becomes even more stable. The energy difference between the 2s and 2p orbital is very small. When carbon atom is ready to form bonds, it gets a small amount of energy from bond energy and gets excited to promote an electron from the 2s to the empty 2p to get 4 unpaired electrons. We have got 4 unpaired electrons ready for bonding, but these electrons are in 2 different kinds of orbitals and their energies are different. We are not going to get 4 identical bonds unless these unpaired electrons in 4 identical orbitals. We can explain that the 4 orbitals of carbon containing unpaired electrons are energetically equal by the phenomenon called hybridization. Linus Pauling, the world's one of the greatest scientists and a great humanist, he was acknowledged as the most influential chemist. He is the only person ever to receive 2 unshared Nobel Prizes, for chemistry in 1954 and for peace in 1962. Do you know? The concept of hybridization was introduced by Linus Pauling in 1931. The redistribution of orbitals of almost equal energy in individual atoms to give equal number of new orbitals with identical properties like energy and shape is called hybridization. The newly formed orbitals are called as hybrid orbitals. Hybridization. In the excited carbon atom, its 1s orbital, 2s and 3p orbitals, 2px, 2py, 2pz intermix and reshuffle into 4 identical orbitals known as sp3 orbital. Then carbon atom undergoes sp3 hybridization. The 4 electrons enter into the new 4 identical hybrid orbital known as sp3 hybrid orbital 1 each, as per Hund's rule. Since carbon has 4 unpaired electrons, it is capable of forming bonds with 4 other atoms. Example: when carbon reacts with hydrogen, 4 hydrogen atoms along their s orbitals containing 1 electron each to overlap the 4 sp3 orbitals of carbon atom at an angle of 109 degrees 28 minutes. 4 orbitals of an atom in the outer shell orient along the 4 corners of a tetrahedron to have minimum repulsion between their electrons. The nucleus of the atom is at the center of the tetrahedron. This leads to form 4 sp3 s-sigma bonds between carbon atom and 4 hydrogen atoms. All these bonds are of equal energy. sp2 hybridization with an example. Consider ethane. Ethylene CH2 forms double bond CH2 molecule. In the formation of CH2, double bond CH2, each carbon atom in its excited state undergoes sp2 hybridization by intermixing one s orbital, that is 2s, and 2p orbital, say 2px and 2py, and reshuffling to form 3 sp2 orbitals. Now each carbon atom is left with one p orbital, say 2pz, unhybridized. The 3 sp2 orbitals, having one electron each, get separated around the nucleus of carbon atoms at an angle of 120 degrees. When carbon is ready to form bonds, one sp2 orbital of one carbon atom overlaps the sp2 orbital of the other carbon atom to form sp2 single bond sp2 sigma s bond. The remaining two sp2 orbitals of each carbon atom get overlapped by s orbitals of two hydrogen atoms containing unpaired electrons. The unhybridized pz orbitals on the two carbon atom overlap laterally as shown in figure to form pi bond. Hence, there exists a sigma bond and a pi bond between two carbon atoms in ethane molecule. Hence, the molecule ethane C2H4 is explain sp hybridization. Each carbon is only joining to two other atoms rather than 4 or 3. Here, the carbon atoms hybridize their outer orbitals before forming bonds. This time they only hybridize two of the orbitals. They are s orbital, that is 2s, and one of the 2p orbitals. Another 2p orbitals are unchanged. So, the new hybrid orbitals formed are called sp hybrid orbitals, made by an s orbital and a p orbital reorganizing themselves. Let us consider ethyl molecule to know the ability of C to form one single bond and one triple bond form. In acetylene molecule, there exists a triple bond between two carbon atoms, and the fourth valency of each carbon atom is satisfied by hydrogen atoms, HC double bond CH. In C2H2 molecule, there are two carbon atoms and two hydrogen atoms. In excited state, each carbon atom undergoes sp hybridization by mixing its one s orbital 2s and one p orbital 2px and reshuffling to form two identical orbitals known as sp orbitals. Each carbon atom has two unhybridized p orbitals, say 2py, 2pz. One sp orbital of a carbon overlaps the sp orbital of other carbon to give sp-sp sigma bond. The other sp orbital of each carbon atom overlaps s orbital of a hydrogen atom to form a s-sp sigma bond. The unhybridized p orbitals of one carbon atom laterally overlap the unhybridized p orbitals of other carbon atom to give two pi bonds between two carbon atoms, say pi py to py, pi pz to pz. Thus ethyl molecule HC triple bond CH, and there exist 3 sigma bonds and 2 pi bonds in the molecule. Allotropes of carbon. The property of an element to exist in two or more physical forms having more or less similar chemical properties but different physical properties is called allotropy. The different forms of the element are called allotropes. The allotropes of carbon are classified into two types. They are amorphous forms, crystalline form. Amorphous forms. Different amorphous forms of carbon are coal, coke, wood charcoal, anema charcoal, lamp black, etc. Crystalline forms. Carbon in solid phase can exist in three crystalline allotropic forms: diamond, graphite, and Buckminster fullerene. As these crystalline allotropes differ in their structure, they possess different physical properties. Diamond. In diamond, each carbon atom undergoes in its excited state sp3 hybridization. Hence, each carbon atom has a tetrahedral environment. The three-dimensional structure of diamond is as shown. As C-C bonds are very strong, any attempt to distort the diamond structure requires large amount of energy. Diamond is one of the hardest materials known. It is a colorless transparent substance with extraordinary brilliance. Due to its high refractive index, it is quite heavy. It has high thermal conductivity and high melting point. Graphite. Graphite forms a two-dimensional layer structure with thin bonds within the layers. There are relatively weak interactions between the layers. The arrangement of carbon atoms in graphite layers. In the layer structure, the carbon atoms are in the trigonal planar environment. This is consistent with each carbon atom in sp2 hybridization. Interactions between the sp2 orbital overlaps lead to the formation of C-C bonds. Each carbon atom is with one unhybridized p orbital. The unhybridized p orbital interact to form a pi system which is delocalized over the whole layer. The interactions known as London dispersion forces between the layers, which are separated by a distance of 3.35 angstrom, are weakened by the presence of water molecules so that it is easy to cleave graphite. For this reason, graphite is used as lubricant and as the lead in pencils. When we write a pencil, the interlayer attractions break down and leave graphite layers on the paper. Pencil marks are easy to remove from paper with an eraser because the layers do not bind strongly to the paper. Do you know? The Buckminster fullerene, or usually just fullerene for short, was discovered in 1985 by a team of scientists Robert F. Curl, Harold W. Grotto, and Richard E. Smalley from Rice University and the University of Sussex, three of whom were awarded the 1996 Nobel Prize in Chemistry. They are named so for the resemblance of the structure to the geodesic structure devised by the scientist and architect Richard Buckminster Bucky Fuller. Buckminster fullerene. Buckminster fullerene are molecules of varying sizes that are composed entirely of carbon. The arrangement of these molecules leads to the form of a hollow sphere, ellipsoid, or tube depending upon their orientation. Fullerenes are formed when vaporized carbon condenses in an atmosphere of an inert gas. Spherical fullerenes are also called buckyballs. These are the purest allotropic forms of carbon because of the absence of free valencies or surface bonds. Buckminster fullerene contains nearly spherical 60C molecules with the shape of a saucer ball. Fullerene 60C molecule contains 12 pentagonal and 20 hexagonal faces on its saucer ball shape, and each carbon atom has sp2 hybridized orbital. Nanotubes. Nanotubes are another allotropic form of carbon discovered in 1991 by Sumio Lijima. Nanotubes consist of hexagonal array of covalently bonded carbon atoms, similar to the sheets in graphite. Unlike the flat graphite sheet, in nanotubes, the sheets are rolled into cylinders. Due to this reason, they are called nanotubes. Nanotubes, like graphite, are electrical conductors and can be used as molecular wires. In integrated circuits, nanotubes are used instead of copper to connect the components together. Scientists inserted biomolecules into nanotubes to inject them into single cells. Do you know? Graphene, the new wonder material. As its name indicates, graphene is extracted from graphite, the material used in pencils. Like graphite, graphene is entirely composed of carbon atoms. For a thickness of 1 mm, graphite contains some 3 million layers of graphene. The carbons are perfectly distributed in a hexagonal honeycomb formation only in 0.3 nanometer thickness. Graphene conducts electricity better than copper. It is 200 times stronger than steel, but 6 times lighter. It is almost perfectly transparent to light. Wieland Friedrich in 1800 to 1882. German chemist who was a student of Berzelius, in attempting to prepare ammonium cyanide from silver cyanide and ammonium chloride, he accidentally synthesized urea in 1828. This was the first organic synthesis and shattered the vitalism theory. Wheeler pursued the matter further and discovered that urea and ammonium cyanide had same chemical formula but very different chemical properties. This was an early discovery of isomerism, since urea has the formula CO NH2 twice and ammonium cyanide has the formula NH4 CNO. Versatile nature of carbon. By the 18th century, scientists tried to explain the difference between the compounds in a broader way. Surprisingly, F. Wheeler in 1828 produced an organic compound, urea, in the laboratory by heating an inorganic salt, ammonium cyanide. Many other chemists were unsuccessful to prepare the so-called organic compounds, methane, acetic acid, etc. in the laboratory. This gave a death blow to the idea that organic compounds are derived from living organisms. After observing the structure and elements of organic compounds, they defined organic compounds as compounds of carbon. Therefore, organic chemistry is totally allotted to carbon compounds. We understand that all molecules that make life possible, carbohydrates, protein, nucleic acids, lipids, hormones, and vitamins contain carbon. Food that we get from nature, various medicines, cotton, silk, and fuels like natural gas and petroleum are carbon compounds. Synthetic fabric, plastic, synthetic rubber are also compounds of carbon. The estimate number of carbon compounds known today is about 3 billion. Catenation and tetravalency properties of carbon. These are responsible for the formation of large number of carbons. Catenation. If any element forms bond between its own atoms to give big molecules, we call the property as catenation. catenation property. Carbon has the ability to form longest chain containing millions of carbon atoms in molecules like some proteins. Sulfur, phosphorus, and some other non-metals have this property, but to a very less extent. You have understood that carbon can form 4 single covalent bonds, a double bond, and 2 single covalent bonds, a single covalent bond and a triple bond, or 2 double bonds with its own atoms or atoms of other elements to satisfy its tetravalence. This ability of carbon to form bonds in so many ways made it as versatile element in nature. Hence, carbon's ability to form largest number of compounds, to show catenation, to form various types of bonds, made it the versatile element. Hydrocarbon. The compounds containing only carbon and hydrogen in the molecule are called hydrocarbons. They are classified into 2 categories: open chain hydrocarbons or aliphatic hydrocarbons or acyclic hydrocarbons. Closed chain hydrocarbons: CH3, CH2, 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 CH3, N-pentane, a straight chain compound. CH3, CH, CH3, CH2, CH3, isopentane, a branch chain compound. CH2, 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 cyclopentane, a cyclic compound or a ring compound. Do all the above compounds have equal number of C and H atoms? In open chain hydrocarbon, first example, you will notice that all carbons are linked to one another, resulting a linear structure. Whereas in the second example, 4 carbons are linked in linear way, and the 5th carbon is linked to the parent chain, resulting a branch. In closed chain hydrocarbon, from example, we find that carbon chain is closed to form a ring. Open and cyclic or closed hydrocarbons are again classified as alkanes, alkene, and alkyne. Alkane, hydrocarbons containing only single bonds between carbon atoms. Alkene, hydrocarbons containing at least one double bond between carbon atoms. Alkyne, hydrocarbons containing at least one triple bond between carbon atoms. Saturated and unsaturated hydrocarbons. The hydrocarbons containing only C to C single bonds are known as saturated hydrocarbons. All alkenes are saturated hydrocarbons. The hydrocarbons that contain at least one double bond, C double bond C, or contain at least one triple bond, C triple bond C, between the 2 carbon atoms are called unsaturated hydrocarbons. Alkenes and alkynes are the examples for unsaturated hydrocarbons. Straight chain, branch chain, and closed chain hydrocarbon compounds may be saturated or unsaturated. See the following examples. Which of the following compounds are unsaturated? Justify your answer. CH3, CH2, CH3, CH3, CH, double bond, CH2, CH, CH2, CH, CH2, HC, triple bond, C, CH, double bond, CH2, CH3, CH, CH3, CH, double bond, CH2, CH3, CH2, 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 CH3. A and F are saturated hydrocarbons because they have only single bonds. Remaining are unsaturated hydrocarbons as they have double or triple bonds. Identify the compounds in the following as branch chain and closed chain compounds. CH3, CH, CH, CH3, CH3, CH2, CH3, branch chain. CH2, CH2, H3C, CH, CH2, closed chain. CH, CH2, CH, CH2, CH2, closed chain. HC, triple bond. C, C, CH3, 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 branch chain. Binding of carbon with other element. Carbon forms compounds not only with atoms of hydrogen but also with atoms of other elements like oxygen, nitrogen, sulfur, phosphorus, halogen, etc. Let us see the compounds of carbon with other elements. Carbon compounds with C, H, X. Compounds containing C, H, X, where X represent halogens like chlorine, bromine, iodine atoms. Example: CH3Cl, CH3, CH2, Br, CH2Cl, CH2I, CH3, CHCl2. These are known as halogen derivatives of hydrocarbons or halohydrocarbons. Carbon compounds containing C, H and O are of different types. Alcohols. If a hydrogen atom of H2O molecule is replaced by R, we get alcohols ROH. The hydrocarbons that contain OH group are called alcohols. Observe the following examples: CH3OH, CH3CH2OH, CH3CHOH, CH3, etc. General formula of alcohols is ROH, where R is alkyl group, CnH2n plus 1, aldehyde. The hydrocarbons with functional group CHO are called aldehyde. Observe the following examples: H, C, H, double bond O, formaldehyde, CH3, C, H, double bond O, acetaldehyde, CH3, CH2, H, C, double bond O, propionaldehyde, etc. General formula of aldehyde is RCHO, where R equals to alkyl group or hydrogen and CHO is functional group. Ketones. The hydrocarbons with C, 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 double bond O functional group are called ketones. O double bond CH3, C, CH3, dimethyl ketone CH3, CH2, C, CH3, double bond O, ethyl, methyl, etc. C, 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 double bond O group is known as ketone group. General formula of ketones is R and R1 are alkyl groups which may be same or different. Carboxylic acid. The general molecular formula of carboxylic acid is RCOOH, where R is an alkyl group or H atom. H, C, OH, double bond O, formic acid. CH3, C, OH. OH group is called the carboxyl group. Ethers. Ethers are carbon compounds related to H2O in such a way that both hydrogen atoms are replaced by two alkyl groups, which may be same or different. Example, CH3O CH3 dimethyl ether, CH3 CHO CH3 ethyl methyl ether, CH2 double bond CHO CH3 methyl vinyl ether, etc. Esters. These compounds are derivatives of carboxylic acid. If the hydrogen atom of COOH gets replaced by R, the alkyl group esters are obtained. O double bond CH3 COCH3 dimethyl ester, O double bond CH3 CH2 COCH3 ethyl methyl ester, O double bond CH3 CH2 COCH2 CH3 diethyl ester, etc. Compounds containing CHN amines. Example, CH3 NH2, CH3 CH NH2, CH3 CH3 CH2 NH2 NH2 CH3 CH2 C CH3 CH3 etc. NH2 group is called amine group. We may compare amines to NH3 as we have done ROH and ROR to H2O. If one hydrogen atom is replaced from NH3 by an alkyl group, we get the so-called primary amines. If two hydrogen atoms of NH3 are replaced by two alkyl groups, same or different, we get secondary amines, and if all the three hydrogen atoms are replaced by the same or different alkyl groups, we get tertiary amines. Example, CH3 and H3C, secondary amine, and methyl methanamine, CH3 and H3C, CH3, tertiary amine, and N-dimethyl methanamine. Functional groups in carbon compounds. The characteristic properties of an organic compound depend mainly on an atom or group of atoms in its molecule, known as the functional group. Organic compounds are classified by the type of functional group they contain. Functional groups are responsible for the behavior of the organic compounds. Compounds containing the same functional group undergo similar types of reaction. Isomerism, the phenomenon of possessing same molecular formula but different properties by the compounds, is known as isomerism. The compounds that exhibit isomerism are called isomers. Iso equals to same. Meros equals to part. That is, they have same molecular formula. Observe the following two structures: CH3, CH2, CH2, CH3, CH3, CH, CH3, CH3. The first one is called butane, or in the common system it is known as N-butane. The second one is called 2-methyl-propane, or isobutane in the common system. We find both of these compounds in nature. They have different properties due to the difference in their structures. In the above example, isomerism is due to the difference in the structures. Therefore, it is called the structural isomerism. Homologous series. The series of carbon compounds in which two successive compounds differ by CH2 unit is called homologous series. Example, alkane, alkene, alkyne, haloalkane. Homologous series of organic compounds have following characteristic features. Successive compounds in the series possess a difference of CH2 unit. They possess similar chemical properties due to the same functional group. Example, alcohol, aldehyde, and carboxylic acid have functional groups COH, CCHO, and CCOOH respectively. They show a regular gradation in the physical properties. The individual members of a homologous series are called homolog. Nomenclature of organic compounds. We have number of organic compounds and they have common names. It is difficult to remember their names individually. The International Union of Pure and Applied Chemistry IUPAC had been formed, and one of its responsibilities is to name the organic and inorganic compounds in systematic order. The basic idea behind the systematic nomenclature is that there should be only one name for the given structure throughout the world, and also there should be only one structure for the given name. The IUPAC name of an organic compound gives information about the number of carbon atoms present in the molecule. We call this part of the name as word root. C1 meat, C2 eat, C3 drop, C4 butt, C5 pet, C6 heck, C7 het, C8 out, C9 non, C10 death, and so on. The substituents in the molecule, which are shown as the prefix. The functional group in the molecule, which is shown as suffix. Prefix. Prefix has parts like primary prefix, secondary prefix, numerical prefix, etc. Primary prefix is cyclo, and it is useful only for cyclic compounds. Secondary prefix for halogen substituents written as halo, alkyl, alkoxy, etc. Suffix. It also contains several parts known as primary suffix, secondary suffix, numerical suffix, and number suffix, etc. Primary suffix tells about CC and C double bond C, N, C double bond C, IN, etc. Secondary suffix tells about functional group with the particular terms. Example, hydrocarbon E, alcohol OL, aldehyde Al, ketone ONE, and carboxylic acid OIC acid. Numerical prefixes di, tri, etc. Numbers are written to tell about to which carbon atoms of the compound the substituent, multiple bonds, or functional groups are attached. The following order is to be followed by naming carbon compound. The order is as follows. Numbers, numerical prefixes, secondary prefix, primary prefix, word root, numbers, numerical prefix, primary suffix, numbers, numerical prefixes, and secondary suffixes. From the above table, 1, 2 are numbers, and numerical designations to be written for secondary prefixes. 3 tell about the position and repetitions of secondary functional groups known as substituents respectively. Example, CH3, CH, CH, CH3, Cl, Cl, 2,3 dichlorobutane. 6 and 7 tell about the position and repetitions of the multiple bonds in the structure of the molecule of the compound. These are related to the primary suffix H that tells about the unsaturation. Example, CH3, C double bond, CH,
Facebook
CH,
lives,
triple
like
bond,
TV channel
CH,
live program.
but 3 in 1 I
దీని
in
కింద ఏది
9
సోషల్
and
మీడియా
10
అకౌంట్స్
tell
మెయింటైనింగ్
about
ప్రాక్టికల్
the
రాసి ఉంటుంది
position
దాని
and
కింద
reputation of the functional group. Our
ఫేస్బుక్ అండ్
principal
యూట్యూబ్ లైవ్స్
functional group 11 in a polyfunctional compound. It gives the
యూట్యూబ్ లైవ్స్
information which carbon represents it or to which carbon the functional group is attached and how many times it is repeated.
లైక్
If it comes only once, we need not
లైక్
write
టీవీ ఛానల్
mono. That
బ్రాడ్కాస్ట్
is, if no
లైవ్
numerical
బ్రాడ్కాస్ట్
prefix is present, it is understood that the functional group is not repeated. Similarly,
టీవీ
in the
ఛానల్
names of
లైవ్
aliphatic
బ్రాడ్కాస్ట్
compounds, word root 5, primary suffix 8, and secondary suffix 11 are definitely present, and all others may or may not be present. Example: CH3, CH2, CH, CH2, OH, OH, butane, 1,2-diol. Punctuation: numbers are
ఎందుకంటే
separated by comma and numbers and designations by hyphen.
మాట్లాడదా
If you find more than one substituent
ఆ
in the
ఇంపార్టెంట్ అయితే
structure,
మనం లేకుండా
you
ప్రపోజల్
have to
ప్రిపేర్
follow
చేసుకున్న ఒక 5 నిమిషాలు
alphabetical order while naming
ఇంపార్టెంట్ అయితే
them.
ఈ 2-3 నిమిషాలు
For
చదివితే
these numerical
హాఫ్ అన్ అవర్ అట్లా
prefixes
పెట్టకుంటే
should
నేను
not be
చెప్పేసుకున్న
considered.
ఒక 10 నిమిషాలు అయిపోతుంది
Substituents
సరే
X
చేసి
halo, R alkyl, OR alkoxy, NO2 nitro, NO nitroso, etc. If you find more than one functional group in the structure, you select the principal functional group and write it as secondary suffix. All other functional groups become substituents. Increasing order of priority, choosing and naming a principal characteristic group. This should be written as secondary suffix. Numbering carbon atoms. We can number carbon atoms from left to right or from right to left, so that some of the numbers indicating the positions of substituents and functional groups should be minimum possible. The functional group carbon should be given the lowest number even if it does not obey rule 1. The carbon atoms of the chain terminating functional group, say CHO or COOH groups, should be given always number 1 even if it does not obey rules 1 and 2. Suffixes and prefixes for some important characteristic functional groups. Class, formula, prefix, suffix. Acid halides. COX, where X is halogen atom. Halocarbonyl, carbonyl halide. Alcohols: OH, hydroxy, OL. Aldehydes: CHO, formyl, carbaldehyde, CHO. Oxo, all. Amides: CONH2, carbamyl, carboxamide, CONH2, oxo, all. Amines: NH2, amino, amine. Carboxylic acids: COOH, carboxy, carboxylic acid, COOH, oic acid. Ethers: OR, R-oxy. Esters: COOR, oxycarbonyl, R-carboxylate. COOR, R-oxycarbonyl, R-OH. Ketones: C-double-bond-O, oxo, on, nitriles, CN, cyno, carbonitrile, CN, nitrile. Examples: CH3, CH2, OH. Principal functional group OH, OL. Parent hydride CH3, CH3. Parent hydride plus one principal functional group CH3, CH2, OH. Name of the compound ethanol. CH3, C double bond O, CH2, 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 OH. Principal functional group C double bond O, on. Parent hydride CH3, CH2, 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 CH3. Heptane. Parent hydride plus principal functional group CH3, CH2, 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 C double bond O, CH3. Substituent OH. OH, CH2, 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 C double bond O, CH3. Heptane to own hydroxy. Name of the compound 7-hydroxy heptane to own. Note, in the solution, the principal functional group C double bond O, keto group is given more priority than to OH alcohol. CH2 double bond CH, CH2, OH, CH, CH3. Parent hydride CH3, CH2, 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 CH3, pentane. Principal functional group OH, OL. Principal hydride plus principal functions pentane. To all. Subtractive modification minus 2H. En. Name of the compound pent 4N 2-ol. Examples: 2-methyl-pentane 3-ol, 2-bromo-3-ethyl penta 1,4-diene, 3-bromo-2-chloro 5-oxohexanoic acid, 3-amino-2-bromo hexane 1-ol, 3,4-dichloro but 1-ene. Solution: CH3, CH2, 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 CH3, CH3, CH2, CH3, CH2, OH, CH2, CH3. H2C double bond C, Br, C, CH2, CH3, H, C, H, double bond CH2. Why do sometimes cooking vessels get blackened on a gas or kerosene stove? Because of the inlets of air getting closed. The fuel gases do not completely undergo combustions. Hence, it forms a sooty carbon film which gets coated over the vessel.
రాసినాం బ్రాడ్కాస్టింగ్ దాని కింద బ్రాకెట్లో ఏం రాస్తామంటే